All right, so I hope you're hearing me and think, if not, this whole life thing would be like a huge fail. But like, so many of you have been DMing me to, what should I say, do a whole past paper run through for the Cape chemistry. So unit 1. So what I had done is I'd actually gone through so many the different past papers and picked out questions based on the different topics sent by CXC. So I did my physics exam yesterday, and I can attest to the fact that yes, only the topics that they said that they would, that would come on it actually came on it. So no worries, no little cheating there. They kept the word. All right. So what I'm going to do is I'm going to go through a couple past papers here. So, if you have a friend that's, going to do Cape chemistry on Thursday, you can tell them to like, forward, because you kind of get free answers here. So let me stop chatting you out because I don't know how long I'm going to be here. I want to finish all the questions that I came up with and get you rolling. So, guys, like, if you have my number and thing, you know that you're not hearing me, send me a message real quick. Wait, it's best I put that in the chat. Give me a second. If you aren't hearing me, send me a message on app. All right, so I'm going to start with this first, and then I'm going to actually show you guys the mock exam that I gave the students that I tutor Cape Chemistry Unit 1. All right. And I actually gave away that mock exam on my Instagram page. So, I had posted, what do you call it? I had posted a giveaway and said that, if the first 5 people to like DM me, you're going to get this paper free, and I'm going to mark it and give you feedback. And so if you're not following me on my Instagram pages, just do me a huge favor and go over to my personal @CAM_EO. My name is Camille, by the way, and follow me there, and follow me at young_genius.official. All right, so let me really stop chatting you out and get into this. All right. So this question was from the 2006 paper 1, and I divided it based on topics and not by the years. All right. And excuse me if you're hearing any, background noises. I'm not home alone. So here we go. A sample of titanium gives the spectrum that's shown in the figure below. So here we have the spectrum being shown, and what they want you to do is calculate the relative atomic mass AR, that is, of titanium. Okay, so what you want to do first is look at the axes and find out like what exactly are they showing you. And right now you can see that it has the percentage abundance on the Y and the mass to electron ratio on the x-axis. And here we see 46, but what's happening here, this goes straight to 50. So what am I going to do with that? You're going to try to determine the scale that they have here. So 46 to 50, and there are like 3 strokes between it. So I can safely say that this would be 47, this would be 48, this would be 49, and this would be 50. All right. So now you know the atomic masses, or isotopic masses rather. So what you want to do to calculate this is multiply the isotopic masses by the percentage abundances and add them up. So this is 8%. You can either write it as 8/100, or how I like to do it, as 0.08, right? And you want to add that to 47 times the percentage here is 7.3%, and that's the same as 7.3 over 100, or 0.073. right? Want to add that as well to this here, 48 times 73.8%, which is 73.8 over 100, or what's this? 0.738, right? Add that as well to 49 times, 5.5% would be 5.5 over 100, or 0.055, right? Add that as well to 50 times 5.4%, which is 5.4 over 100, or 0.054. Okay, you put all of that into your calculator. Let's do that. And I need you guys to follow with me. You need to exercise some muscle memory. So don't just sit there, staring at the screen. Get your books out and start writing, right? So 47. And by the way, I am seeing the chat. So if you have any questions, you can leave it there and I'll most definitely get to them. All right. So that 48 multiplied by 0.738. Or if you want, you could have just put 73.8 over 100. Hold on, excuse me. All right, sorry about that. I was at 0.738 plus 49 multiplied by 0.055 plus 50 times, what's that, 0.054. And the raw data you get from your calculator is 4793 over 100, which in decimal is 47.93. All right, so that would be the relative atomic mass of titanium, 47.93. You should be okay for that. All right. Now, they want you to use the data booklet and the mass spectrum above to determine the number of protons and neutrons of the most abundant isotope of titanium. Now, the most abundant would be the one with the biggest percentage, right? So here off the bat, we can see it's 73.8%, and that would correspond with the one with isotopic mass 48. Yes. So we know that titanium 48 is the most abundant. Now, the atomic number of titanium is 22. So first of all, the number of protons would be the same as the atomic number, so it's 22. So we know it's 22 protons, but the number of neutrons would be the mass that we got here, 48, minus the number of protons, right? So it would be 48 minus 22, and that would give you 26. Let me put that in the calculator to just be sure I don't trust myself. Yes, it's 26. And just like that, you'd have gotten your 3 marks, right? Easy, easy. Now, here they want us to use the SPDF notation to write the electronic configuration of titanium. All right. And let's say that we're not going to use F. So F is a distractor because titanium is a transition element, right? So it stops at 3D. And ensure that you know the definition for a transition element. It will help you to make your deductions when they ask you questions to state trends, pick up on stuff like that, okay? So first we want to start with the first quantum level. So 1s, and 2 electrons go go in the S. So 1s, 2, 2s, 2 as well, 2p, 6. And so far that's 10 electrons gone from the 22. We're going to 3s, 2, 3p6. No, we fill the 4s before the 3d, so just let's write 3d, but then 4s, 2, and add that up. It's supposed to be 20, but we need 22, so just add the remaining electrons in the 3d, and that would be 2. That would be an electronic configuration for titanium in, you know, the SPDF notation. All right, take a breather. We're just getting started. You need to draw the shapes of the orbitals that are in the principal quantum number equal, where n is equal to 2 in the titanium atom. In the quantum level, n equal to, we know that we had 2s2 and 2p6. So we had what we had were s orbitals and p orbitals. So you want to draw those. All right. So first of all, the s orbital. The s orbital is spherically shaped. So you want to draw your axis, you know, x and y. And forgive me, I know the circle is going to be so bad. I told you. All right, fair enough. It's supposed to be a sphere or a circle, all right? And now the p orbitals, they're described as being dumbbell shaped, and this is in 3 dimensions. So I'm going to drop my 3 planes here. Right? And let me change the color of this pen so you can see what I'm doing. This is one p orbital. This would be another. And this here would be another. And what we have is the px, the py, and the pz. And you'd be done there, and you'd have gotten your 2 marks. Okay? Now, the next one. It says that another isotope of titanium, they're giving us titanium 51, right? It says it decays by beta emission. A beta particle has no mass and a single negative charge. So here they're telling you what it is. So if you didn't remember, now you know what it is. I want you to write an equation to represent the decay of the titanium 51 atom. Now we know that it underwent beta decay. So first of all, I want you to write down the atom. So titanium 51, right? Now, all your equations need an arrow, so ensure that you put that. It probably seems silly for me to say this now, but for real, what's wrong with me? Really and truly, like when it comes down to exams, you can't take anything for granted. You need to pay attention. Don't say that, oh, I know this already, so I can't make that mistake, right? I can't make that mistake. I'm not seeing anything. Is there anything in the chat though? Give me a sec, let me refresh the chat and see something. Oh, of course, there are questions there. So why am I not seeing it on this phone? Oh my God. Sorry about this live chat. Okay. Oh yeah, for the question where Let me go back up to it. For the question where we worked out the relative atomic mass, yes, you can round off, but I wouldn't advise it. At least leave one, decimal place. All right. And I am guessing for the question, can we draw it on one? I'm thinking you're asking about here when we're asked to draw the orbitals. No, you have to separate them. Can't draw everything on one thing. You have to separate them or you're not going to get your marks. No, back to this. Titanium 31. No, after you put your arrow to represent, what the change is, you want to put the symbol for what type of emission we're going to be dealing with. And in this case, we're going to be dealing with beta emission. So what you'll have is the E, which stands for the electron, because they said that the beta particle is an electron. So no mass and a -1 charge. Right? Negative charge, so you put it as -1. Now, let me show you how you can most definitely know if your answer correct. Like, you're not asked, Christ, if your answer right when you see this. All right, now look here. We have 51 over here as the mass, and we know that this is supposed to be 22 for the atomic number, right? Now, whenever you look over here, the sum of the things over here should be equal to the sum on the other side of the arrow, right? So you have 51 as the mass number here. The mass number over here has to be 51. And 0 plus what would be equal to 51? 51, right? Now here we have -1. So you want to ask yourself, -1 plus what will give you 22? And if you want, you can do the whole transposition thing, and you'll find that your little question mark here will be equal to 22 plus 3 plus 1 plus 1. All right. So you'll find out that here you would have the atomic number being 23. So you know that now whatever is 23 on the periodic table, that would be your new atom, right? So vanadium has the atomic number 23. So, you can tell that that would be it. Now, let me explain a bit more what I meant by the sum of everything being equal on both sides. All right. Now, here we have 0 for the atomic number, for the mass number, plus 51, and that will be equal to 51, as you can see here. Now we need 22 for the atomic number, and we have -1 plus 23. A negative number and a positive number, you're going to subtract the numbers and actually keep the sign of the bigger number. So you're going to subtract 1 from 23, and that will give you 22. And since 23 is the bigger number, you know that, the sign is going to be a plus sign or the positive sign. So that's how you know if you're right. So 22, 22, 51, 51. Your answer is correct. All right. So I guess we can move on. All right. So this says the atom of certain elements contain nuclei in which the ratio of neutrons to protons is greater than 1. All right. So these nuclei tend to emit radiation in order to bring the ratio closer to 1. And I've said this in countless videos. Like this here, I'm sure you've seen this graph with neutron to proton, and then you see some little fancy dots here, and they call this the concentrated area of dots the band of stability, right? And what they want is for atoms to fall within this area to be stable. But really and truly, what it wants is the atom to have a neutron-proton ratio that is closest to 1. So you would get this directly proportional linear line, you know? Anyways, now they want you to describe the 3 types of radiation that an unstable atom may emit. And there are many. I don't know why they just said 3. I know why they said 3, because there are only 3 on your syllabus that you need to know. So in your answer, the symbols and penetrating power of each type of radiation, you know, you have to put that. So the first one we can talk about is, let's say, alpha particles. Right? The symbol for this looks somewhat like this and looks like an A to me. Forgive me for my terrible writing. And it's a helium nucleus with, you know, mass number 4 and atomic number 2. And the penetrating power, let's talk about that last. We also have beta particles. Right? And there you go. That would be the symbol. And you have E0 minus 1. Right? And you have gamma radiation. And that kind of looks like a Y, something like that. Anyways, can represent it as this as well. Now let's talk about penetrating power. In the order that I have listed it, it has the penetrating power is from low to high. So this has a low penetrating power, right? This has moderate, that's beta particles, penetrating power. And gamma has extremely high penetrating power, right? So alpha particles are stopped by things like paper. This here, beta particles are stopped by things like foil, while gamma rays are stopped by lead, things like lead, right? So keep that in mind and you should be fine. And that was from the 2015 paper, by the way, paper 2. Now, this question repeated. All right. Americium 241. So you know that that's the atomic mass that you'd be working with. Decays via alpha particle emission. All right. So we're told that it emits, you know, an alpha particle, which is this helium nucleus. So they want you to write the nuclear equations. Pay attention to this as an S. So you're required to write more than 1 equations to show the new element that forms when an atom of americium 241 decays via the emission of 2 alpha particles. Okay. So let's start with the first emission. Let's just say number 1 for now. You have americium 241, and they paid you the courtesy of giving you, you know, the atomic number, which is 95. I think you're going to have to use a data booklet to find out the other ones or the results if you don't know the periodic table like that. Anyways, so this here, remember your arrows. You want to put the helium nucleus, which represents the alpha particle being emitted. And remember, I told you that the sums on both sides of the arrows, they have to be equal. So you have to have a mass number of 241 on the other side and a total atomic number of 95 on the other side. So you know that this is going to be plus. So what you want to ask yourself is what plus 4 gives you 241? That's why you actually subtract 4 from 241 when a particle undergoes alpha decay, right? So 241 minus 4 give you 237, and that would be a new mass number, right? And the atomic number would decrease by 2, because you want to ask yourself, what plus 2 gives me 95? What now, Jesus? And that would be 93. Now, you want to find out which atom on the periodic table has an atomic number of 93. And that's Neptunium, symbol NP, all right? Now, remember they asked you for 2 equations because it underwent alpha decay twice. So you want to start now with your second emission being NP 23793. All right. And remember your arrows. Remember to rewrite your your particle, you know, that's being emitted, whether it be gamma, beta, whatever, right? Now 4 to decreases by 4, so you want to subtract 4 from 237. I'm going to continuously try to drill this in your heads. What plus 4 is equal to 237, right? And that's 233. And then you want to ask yourself, what plus 2 is equal to 93? And that's 91. Now which element on the periodic table would have, you know, the atomic number 91? That's protactinium. It's Pa. So if you write those 2 things, you get your full marks, right? That's all you have to do. Now, let's continue. Who says they don't repeat questions on past papers? Isn't this fancy? 2015 paper 2 wants you again to draw the atomic orbitals for the principal quantum number 2 and include the X, Y, and Z axes in your, drawings. So first you have your S orbital. Right? And it's spherical in shape, so remember that. Then your p orbitals. And remember it has a p orbital has 3. Yep. 3 suborbitals, right? And it's in 3 dimensions. So you want to draw your planes. Bro, behave. Yeah. You want to draw your planes, and of course you won't have any color switching going on in your exam, but I'm just doing this so you can see, right? So it's dumbbell shaped. And you want to remember to label your axes, right? So this would be X, Y, and this would be Z. X, Y, and this would be Z. X, Y, and this would be Z, all right? And you're all good. And remember to label below it what it is. So this would be the PX, this would be the PY, and this would be the PZ. And you are totally okay to get your marks, right? Because you remember the goal in this is to get as many marks as you can possibly get, right? So you want to do your paper carefully. Like, know your strong areas, because for me, I don't finish the papers, but I ensure that the ones that I do know how to do, I do them properly so that I'll get marks for that. so that the ones that I don't know, I actually guess, but guess rubbish. I don't really lose too much from that. So, the way you know well, and as my coach would say, get marks where you forget. Get where you forget. You know, say you can get that. So why not spend the time and actually get what you know you most definitely can get? Then try figure out the rest after. Right? So here says comment on the similarity and the difference in the electronic configurations of K, that's for potassium, SC is for scandium, and a Zn2 plus ion, which is a zinc 2 plus ion given below. Now, you want to examine the different electronic configurations given. And the first thing I would look at are the orbitals, because that's easiest to see. So I can see that they all have s orbitals, they all have p orbitals, they all have, that would be a lie, they don't all have 3Ds, and they don't all have 4Ss. Whoa, that sounds funny. So the first similarity that I would pinpoint was their arrangement is similar up until you get to the 18th electrons, or up until the 18th electron. So they all have an argon core. And you can further explain this saying, because the arrangement of the first 18 electrons are similar or the same, whatever you want to say. I don't know if you can tell that I'm having fun. Oh Lord. No, that's the only similarity. But if you say any more, you can always, fly down in the chat. Let me see the chat getting active so I can know if it's actually working. So differences. Let me just put similarities for those who are late. Right? Differences. I think I pointed it out when I was talking because I'm a little blabbermouth. But they don't all have 3D orbitals, like potassium doesn't. So K has no 3D, 3D orbitals. And the zinc 2 plus ion, it stops at 3D. So it, Zn2 plus has no 4s orbitals, right? And I guess you get your marks for that because there were only like 3 things. I think it was a 3 marks question. So I don't think you had to write anything else to actually get, all your marks. So that would be well, all right for you. And say, you get your marks and your grade are going to set good. All right. No, this was what? 2017 paper 2. And it wants you to, what is it? Dalton's atomic theory suggests that all atoms of a particular element are identical and atoms of elements are indivisible. So they want you to state 2 pieces of evidence that leads to the rejection of these claims. Yes, I'm going to save it. But YouTube kind of funny, they want me to, it's going to take a while. It won't upload immediately, but most definitely before your exam. So probably later this afternoon, it will be up. So yeah, I'm going to post the live. No, it wants you to state 2 evidence that leads to the rejection of these claims. All right. So we know that Dalton was a big man in the whole atomic theory thing. He came up with it in 1803, I think. Yeah, 1803. You can check my date. It's probably wrong, but I say that confidently, it's 1803. All right. So he came up with his, I think it's 5 or 4 postulates, 4 to 5 postulates And most of them were negated. Like, we find out later in life that, hey, you said this was it, but that wasn't it, bro. So no, we have to be examining how, what went wrong with what he said. Because at one point, everybody believed this to be true. So why is it not true now? So that's basically what the question is asking you. Where did this brother fall short? Where you fall short, brother? All right, so this says all atoms of a particular element are identical. That's not true. Why isn't this true? All right, I'm going to label this because I'm lazy. Of course, ensure you answer your questions in sentences, complete sentences, like well-developed sentences. Right? Number one, not true because isotopes exist, right? And the evidence for this is that on the periodic table, you will see that you'll notice that the relative atomic masses are actually decimals and not whole numbers, right? And this is telling you that the relative atomic masses are actually an average of the isotopic masses, right? So that's what would give you your little evidence that, all atoms of a particular element are in fact not identical, right? So that's the first evidence that, led to the rejection of that first claim there. Now, the second claim that atoms are indivisible. When you think about this, like, because we can't really see atoms, like chemistry is about your imagination. So it's what you can actually infer in space. So how can we know that they aren't indivisible? Well, firstly, we have subatomic particles, right? We do have subatomic particles. It's kind of suggests that you can break them further into electrons, protons, and neutrons. And also, we learned a bit about what we call radioactive decay, right? So by radioactive decay, we can split these things. We can split atoms and we can, go through the process of nuclear fission, right? All right. So yes. So those two pieces of evidence would actually, help you to answer that question. So it's best, if you don't know all of Dalton's postulates, swat them out. They're not hard to learn. You can learn them before Thursday. Swat them out. Ensure that you know them. All right. They aren't hard to learn, so might as well you're going with like extra knowledge. Okay, so those are most of the questions. Like the questions are similar, so I didn't want to do all the past paper questions on each topic because, that would be me repeating myself all day and that would kind of get tiring for you guys and I don't want to wear you out, right? So now we're going on to what is the mole concept. Yes, that was a topic on your broad topics thing. So this says, in an experiment to determine the empirical and molecular formulae of a hydrocarbon. Now this is a big hint, right? Hydrocarbon, the word hydrocarbon, you can divide it into hydro, and that's representing hydrogen, right? And carbon speaks for itself, the element carbon, right? So a hydrocarbon only has hydrogen and carbon, no oxygen, right? All right. So the hydrocarbon is completely burnt in excess oxygen and the products were collected, right? And the products would be carbon dioxide and water. I'm going to show you something later in this session to figure out your products for combustion analysis, right? Because most times on the past papers, the mole concept question is a combustion analysis question. So A gave 3.52 grams of carbon dioxide and 1.62 grams of water on combustion. They were nice. They gave you this, so you don't have to calculate it, the molecular masses. So they want you to calculate the mass of carbon in 3.52 grams of carbon dioxide. All right. Now, carbon dioxide has a molecular mass of 44, right? But they want to just know how much carbon would be in 3.52 grams of, carbon dioxide. So carbon has a what? Atomic mass of 12 out of the total, which is 44 for the relative molecular mass, right? And you want to find that, out of 3.52 grams, right? It's like percentage, except it's not percent. So once you do that, what you'll find is, if you put that in the calculator, you're going to get 0.96 grams of carbon, right? So keep that in mind. Now for hydrogen, you're going to do the same thing. We know that the molecular mass is 18. So hydrogen is H2O. Therefore, hydrogen is like 1 gram times 2. That will give you 2 grams. So you're going to put 2 out of 18 times 1.62 grams of water. All right. And if you put that in your calculator, you're going to get 0.18 grams of hydrogen. All right. And that's completely fine. And you'd have gotten 1 mark for that, the first one, and another mark for the second one. Now, it wants you to use the answers obtained in AI and AII to calculate the empirical formula of A. Now, the empirical formula is the simplest, atomic ratio in which the element will exist, right? So what we want to do is use the masses of each thing found to actually calculate the mole ratio, right? So we have carbon because it's a hydrocarbon. I like to do this. I like to divide it in a table. It helps me to keep track of what I'm doing, right? We know that 1 mole of carbon is equal to 12 grams. Now, some number of mole of carbon will be equal to 0.96 grams. And to be honest, I'll be very disappointed if you guys aren't writing. Like, I'm telling you, write, it's going to help you. So what you want to do now is cross multiply. So you're going to have 12 grams times, number of carbon moles that we need to find times 0.96 grams times 1 mole, all right? We want to divide by 12 grams on both sides, all right? And you'll see that the moles would be for this 0.08, right, moles. You want to do the same thing for the hydrogen. So 1 mole of hydrogen is equal to 1 gram, right? So some, number of moles. Oh, this here is probably see me use it a lot. It means number of moles. So I'd usually just write number of moles and the subscript for whatever I'm finding. So H is equal to 0.18 grams, and that's what we found. We'll find that the number of moles of hydrogen is equal to 0.18. If you don't believe me, do the whole cross multiplication thing. But you're going to end up dividing by 1 and you're going to get by the same thing, right? Now, to find the simplest mole ratio, you want to divide by the smaller number of moles, all right? So in this case, 0.08 is way smaller than 0.18, and it doesn't even matter that I said way smaller. It is smaller, so it's the smaller of the two, right? If it were 3 and 0.08 was the smallest, you'd use 0.08, all right? So 0.08 divided by 0.08 and 0.18 divided by 0.08, right? here you're going to get 1. And for this here, you're going to get 2.25, which you can just simply round to 2 because you're going to use whole numbers. You can't use the, you can't use the decimals for the thing. So the empirical formula for this is CH2. This is actually the empirical formula for alkenes. Now, let's see what the other part says. All right, so here we go. An experiment, it's the same thing. They said that the molar mass of A is 114 grams per mole. They want you to calculate the molecular formula. What you're going to do to calculate this is you're going to divide the molar mass by the empirical formula mass. Right? In this case, the empirical formula mass would be the total mass here that you get for CH2. So 12 plus 2, because 2 times 1 for the hydrogen is 2. So you'd get 14. And they told you that the molar mass is 114 grams per mole. So 114 over 14 going to give you 8 point something. But you can use the solid number 8, right? Now to find the molecular formula, what you want to do now is multiply the empirical formula by, the number that you got when you divided it. So this now, the molecular formula would be equal to C8H2. That's foolishness. H2 times 8, which is 16. All right, so your molecular formula would be C8H16. All right, and that would be it. Now, I don't know if this is still a part of your syllabus. What year is this? 2006. But they want to describe simple tests that could be used to confirm that the products of the combustion of air, water, and carbon dioxide. For water, you can use the cobalt chloride paper, right? And that would turn what? Would turn from blue to pink. This can help you with your transition elements aspect. Think cobalt, one of the cobalt ions is blue, and then when it's reduced, it turns pink. You can read up on that. All right, and for the carbon dioxide, you can use lime water. They use that mostly when we're doing photosynthesis. So lime water, and that would turn white, real cloudy white, I guess, in the presence of carbon dioxide. And you're done. Get 4 marks. All right. No rates of reaction. All right. This wants you to explain what the rate law is. The rate law is also known as your rate equation. All right. So that would be, an example would be rate is equal to the K, because we need a constant times the concentration of reactant A. That would be a rate law or a rate equation. So the rate law, this shows the relationship between the rate C4 H9. No, oh my God. For your question, Natalie, the empirical formula I got was CH2, but I can work it over. I'll work it over later and see if I did something wrong. But all right, let's continue with this. So the rate equation shows the relationship between the rate, right, of the forward reaction or the forward reaction would also be the initial reaction. And the concentration or pressure of the reactants. All right. And now let's say explain, what the order of the reaction would be. Now the order of the reaction would be the power by which the concentration of the reactants are raised and the rate of the reaction actually depends on that. All right, so that would be the order. So if you had said here 8-1, that would be first order with respect to A, and the overall order would be 1, and we'll get to that soon. Now part B, I to BIII refers to the following reaction. AX plus BY gives the products, right? And it wants you to write an expression for the rate law. So in this case, the rate you can say the rate is equal to K, concentration of X, raised to some arbitrary power. You can say A, or the concentration of B to some arbitrary power, and that would be all right. Let's say, sorry, not B, but Y, because Y would be the reactants, right? No, that would be okay, I guess. Now write an expression for the overall order of the reaction. The overall order of the reaction would be the total or the sum of the orders with respect to each reactant. So basically the order of the reaction or the overall order is equal to A plus B, depending on what you had used for, your powers. Now, the overall order of the reaction was found to follow second order kinetics. So they want you to deduce the units of the rate constant, and the rate constant is K, right? For the reaction. So you know that your thingy would be, or your rate law would be rate is equal to K times some products, some reactant, sorry, let's say a second order. I didn't write back the equation up top because I don't have to. I just need something for you to look at. Now, the units for this here reactant would turn out to be mole squared per dm to the -6. How? because you'd have mole per dm cube squared, which is the same as mole per dm cube times mole per dm cube, right? And that's how you would get mole squared per dm to the minus 6 times K, and that's equal to the rate, and the rate, the unit for rate is mole per dm cube per second. Now bring this over here. So you want to divide by mole per dm to the minus 6 on both sides. So mole squared per dm to the minus 6. What you'd see happening now is right here. Mole per dm cube will cancel down here, and you'd be left with mole per dm cube on the bottom. Now, seeing that it's on the bottom, what you want to do is flip these when you're writing it. So you would end up writing K being, the units for K being equal to mole or per mole, or let's write dm first. It doesn't really matter. It's really what you think you're more comfortable with. So you could write dm cube per mole, or per mole dm cube per second, or dm cube per mole per second. Any order you write it in, it's correct. So yeah, all right. No, oh my God. Sorry. Let's move down. This wants you to define the following term. Standard electrode potential of a half cell. Now the standard, what's a half cell? First of all, look at it. What's a half cell? Now the half cell is just one of these things here when you're doing redox equilibrium, right? So the standard electrode potential of a half cell is actually the electric potential. Spelling though. Yeah, sure. On your syllabus, it falls under chemical or lines, that's redox equilibrium. Potential. Should I not? It's not a part of the topic. I'll skip it then. Okay. So let's do the buffers question then. So here, they say a buffer consists of H2PO4 minus and HPO4 2 minus. And it helps to control the pH of what is physiological fluids. And many carbonated soft drinks also use this buffer system. So using the buffer system mentioned above, describe how the solution maintains an almost constant pH, even when small amounts of acid or alkali are added to the solution. All right, my God. No. No. Oh my God. All right, thank you for that. So for the buffers, like I say in broad topics, me look on buffers dede. Hello. All right. So let me look at the broad topics real quick because I won't get this. Chem unit 1. All right, great. So buffers. Jaja. So here, when you add a small, let's deal with the acid part first. So when you add small amounts of acid, what you're going to be doing is practically adding H plus ions to the solution, right? So you can think about this as H, let me write this properly. You're given this HPO4, 2 minus in its aqueous state. Let me hide this. Hide floating meeting controls. All right. I got that done and out of the way so it can stop blocking you. So HPO4 2 minus aqueous plus an H plus ion would actually give you this H2PO4 minus, of course, in its aqueous state. That's the first thing. Now, if you add H plus ions to the solution, what will happen is the equilibrium will shift, and what will be produced is more H2PO4 minus in order to get rid of the H plus ions that you added to the solution, because this whole principle is based on Le Chatelier's principle that if you disturb a system, what the system is going to do is try to combat it and restore its equilibrium. So by adding acid, you're adding H plus ions to the solution, right? And so the system will try to get rid of the excess H plus ions that you added to the solution. So it will shift to the right? And so more H2PO4 minus will be produced. However, if you add an alkali to the solution, you'd be adding H plus ions to the solution, OH minus ions, sorry, to the solution. And what these OH minus ions will do is react with H plus ions, and when they react with the H plus ions, you will get H2O, right? Which is water. And what this does is it removes H plus ions from the solution. So to combat this, what the system will do is restore the H plus ions that were lost by having H2PO4 minus dissociate into HPO4 2 minus and H plus ions. All right. I think you guys I am way ahead of you guys. Like, seriously, I am far ahead of you. So I think that's the whole confusion. It's lagging. So I am seeing your chats when I am far past that. So when I saw that's not coming on the exam, I was way ahead of you at buffers. But yeah, this is what's happening. Let me text one of you real quick because I think I have some links with each other anyways. So you just can't hear me yet. All right, so that's basically what would happen. And if you just explain all of this, it will be totally fine and you get your marks. All right. All right, now group two. And here we go. All right, so a fully filled, let's see. The atomic and ionic radii of the group 2 elements gradually decrease down the group. And that's true. As you go down group 2, the atoms get bigger. Now, outline the reasons for this trend. Now, first of all, the first thing you can talk about is the shielding or screening effect. All right. So what is happening is, as you go down the group, you're practically, let's say, adding a shell, right? By adding a shell, you have these actually being filled, right? And so the electrons here are actually shielding the outer electrons, or what we call the valence electrons, from the positively charged nucleus, right? And through this, the valence shell is allowed to spread a bit further away from the positive nucleus, hence why when you get down, as you go down, it's getting bigger. Also, by the addition of electrons, there are what we call, because you know that like forces attract, right? Like forces repel. That's a lie. Like charges repel. And unlike attracts, all right? And so electrons are negatively charged. So the negatively charged electrons will actually repel the valence electrons, which are also negatively charged. So it will cause, this to spread a bit bigger. Or yeah, that's another reason why group 2 elements gradually, the size of the atoms or the ions gradually increase down the group. So you can say electron repulsion, I guess. And also, that's it. Sorry. This was from the 2015 paper 2. Now, account for variation in melting points of the group 2 elements from magnesium to barium. Now, first, what you want to do is identify whether the melting point increases or decreases down the group. Now, there's a slight increase in the melting point from magnesium to calcium, and then there's a general decrease from calcium to barium, right? So increase from magnesium to calcium, all right? And then there is a general decrease from calcium to the last one, barium, all right? At the end of this paper, I'm going to give you guys a quick break. So I'm going to actually cut it, but can I use the same link? Jesus, I didn't test this. All right. So as the atomic or the ionic radii increase down the group, you will see that there is less attraction between the ions and the delocalized electrons, and thus the melting point would decrease, right? And you will also find that there is less energy that you would actually require to melt the metal. All right, so let's look at this trend. Now, magnesium to calcium increasing. So let's say Mg to calcium, but then from calcium down to barium, you have it actually decreasing. increasing melting point is basically telling you that more energy is required to melt this, while the decrease is telling you that less energy as you go down is required to melt it, right? So that's the variation in the trend. All right, not seeing anything else in the chat. So table 4 shows the observations when 0.1 mole per dm cube solutions of the metal ions are treated with 1 mole per dm cube of sodium ethanoate, and they want you to account for the trends indicated in the table. Now you see in a solution of group 2 cations at 0.1 mole per dm cube, you have Mg2 plus, you have Ca2 plus, you have strontium 2 plus, and barium 2 plus, right? And you can observe that there was no precipitate, then calcium, you see thin white precipitate, then strontium, you see white precipitate, and barium 2 plus or barium 2 plus, you see a thick white precipitate. Now, first, you need to figure out what this question is dealing with. And if you look at it, you can see solubility, like really think about it, it's solubility, because the ones that are, no, they aren't, they're CXC questions, past questions, not Cambridge questions. So these, what was I saying? Thick white precipitate, yeah. So the ones that have, like the thick white precipitate versus no precipitate, those would be less soluble than, you know, the one with no precipitate, right? So how you can account for the trend in solubility here is that the large size of the sulfate ions and the slight increase in the size of the cations result in small decreases in the lattice energy, right? And I'm going to explain this a bit more when I go through my mock paper that I actually wrote. So let's pick this one for now, because it's going to come back and I have a whole, you know, graph to show you what's happening. However, variation in thermal decomposition of the nitrates. Now, metal nitrates are more thermally stable as you go down the group. That means that magnesium nitrate is less stable than the nitrate for barium, all right? So as you go down the group, the thermal stability of these ions increase. And what that means is that by adding heat to it, it's not going to decompose or break down, all right? And this is due to the sizes of the cations, because as the sizes of the cation, as you go down the group, the sizes of the cations increase because, you know, atomic radius increases as well. So the size of cations increase going down the group, all right? And this makes them difficult to be polarized. And that is the NO2, the NO2 minus ion, right? So as it gets bigger, there's a disruption. There's a disruption in bonding. So as you go down the group, what you will find is that the cations will increase, and thus it will be harder for the NO2 ions to be polarized. And this will account for the stability of barium, the barium nitrate versus like a magnesium nitrate, because by adding heat to magnesium nitrate, it will more readily decompose than if you added heat to barium nitrate. And that's basically what it's saying about, you know, the whole thermal decomposition thing. So let's see what, there's nothing after this. So of course, there's going to be another paper, like my mock paper. You can go run, get some water or something, but I'm going to run straight into it, to be honest, because I have another session after this. All right, so like, let me sip some water and then, you know, we start the other paper. All right, I told you it was going to be no long break. I'm so sorry. But like, if you come back and just hear me talking, the recording will be there, so you can just watch it over. So this paper is the paper that I gave the students who I am actually tutoring for CAPE Chemistry Unit 1. So don't mind the whole A-level thing, because CAPE is like advanced proficiency, I think. Yes, it's the advanced exam, so it's similar to A-level, so that's why it has A-level there. Don't be alarmed. Now, this is a mixture of past paper questions and actually modified CXC past paper questions, because I didn't want to give back, you know, the exact question, because I don't like to do that. So for this paper, I actually altered some of the questions for the students who actually work with me. And I actually gave this paper away on my Instagram. So, you know, again, if you're not following me on Instagram, head over to my page, please. Let me just write it down real quick. You can hit me up on my personal page at _CAM_EO. My name is Camille, by the way. And here, young_genius.official. All right. And yeah, you'll find some stuff that would probably be useful to you. I said probably because it's not useful for everybody, depending on the subjects that you do, right? But I'm really working on getting my website up where you can get a lot of other resources. But bear with me, I'm only one person and I'm trying my best. Unit 2, I want to, but I can't promise because I'm dealing with my exams as well. But you know what? I'm going to work towards it, most definitely. I'm going to work towards that Chem Unit 2 and Communication Studies, because it's going to benefit me anyway. So myself as well, right? So I'll definitely work on that Chem Unit 2. All right, so here we have, Jesus Christ. No, this was a past paper question. I didn't alter this any at all. So it says each element, and it's only 1 mark. Each element has a characteristic fingerprint line emission spectrum. Now, Niels Bohr in 1913 proposed an explanation for the emission spectrum of the elements. It wants you to state the property of elements which is responsible for the characteristic line spectrum of each element. Now, the property, at first when I saw this question, I was quite confused. I'm not going to lie about that. But then I thought about it, and I think the property is the presence of different quantum levels, because that's how you actually figure out the different line spectra, right? By the fact that there are different quantum levels. I'm gonna just write that down real quick. Why this get so fat all of a sudden? Pressure sensitivity turn on. Sure. All right, so what happens is, let me just draw a little diagram. That probably, all right, here's our atom, right? What you'll find is high energy photons of different wavelengths, different frequencies will come in and be absorbed by this electron, right? The electron will become excited and it will move to a higher energy state or another quantum level, if you may, right? And when the atom, the electron there loses its energy, so kind of shoot out back another photon, right? It doesn't have to be the same energy, right? And it doesn't have to be the same wavelength or frequency that it absorbed, right? But by emitting, that's where the whole emission comes from. By emission or by emitting that photon will correspond with a certain frequency that will eventually, also correspond to wavelength, because wavelength is inversely proportional to frequency. So as the wavelength increases, the frequency decreases, or as the wavelength decreases, the frequency increases. So remember that. So it will correspond with a certain frequency or wavelength that will actually be show correlation with some part of the electromagnetic spectrum, and thus you will show as emission lines in the different series, like Paschke, Balmer, like Lyman bracket. I think you something there, but the syllabus only requires you to know to an extent about the Balmer series and how it relates to hydrogen and the different energy levels. No, so basically by just stating that the presence of different quantum levels, you should get your mark. Then I asked the students to sketch me a diagram of the line emission spectrum of hydrogen, and on the diagram I wanted them to indicate the direction of increasing frequency and increasing wavelength. All right, so let me just go to advanced real quick and draw myself a box. Here we go. So here we go, box. And on the box, what you want is, you'll see that, all right, one line, probably another one, so space, but as you go out, you're going to have the lines get closer and closer and closer and closer, closer. All right, I'm gonna stop now. Now, this direction would be increasing frequency, and this direction would be increasing wavelength, right? And how you know this? Well, I don't know if this worked when I was teaching them, but I was saying, imagine a fox running over and jumping over fences, right? The further the fences were from each other, the more time the fox would have to run between fences and actually jump, right? So he would be jumping less frequently. But as the fences got closer and closer together, the fox would find that he would have to jump more often. So hence an increase in frequency as the length between those fences got smaller, right? So that was the analogy I used to try to get kids to understand. All right, so if you drew this, you'll get your marks. All right. Now explain in terms of electronic transfer the origin of lines in the Balmer series. Now, first thing, I want you all to know, if you don't state that electrons move from high energy levels to n equal 2 specifically, you're not get your marks. That's what characterizes the Balmer series, right? So here we can say that electrons will absorb high energy photons. I'm not going to write everything. I'm just going to write in shorts, I guess. So electrons will absorb high energy photons, right? And through that, they become excited. And eventually, these electrons will lose energy. And of course, we call this de-excitation. So de-excitation would occur. And through this, we can observe the spectral lines in the Balmer series when electrons fall from higher energy levels. It's also fine if you say quantum levels, right? To the n equal to quantum level. All right. And through stating that, you get your marks. Now, state the region of the electromagnetic spectrum in which the lines in the Balmer series occur. And for hydrogen, this is the visible light region of the electromagnetic spectrum. So that's 1 mark. And you're good. All right. I am flying through this paper. All right, this should be per second. Let's just put that in there for now. Now calculate the energy of a quantum of radiation, which is with a corresponding frequency of mu, where it is equal to 4.57 times 10 to the 14 hertz. Now hertz is per second, right? So that's a lie. That should have been seconds. It's correct. Now, you're going to use the equation E, where the energy is equal to H mu, and this is not V, so don't call it V, it's mu. It's a Greek letter that represents frequency. Now, here they gave you a value for Planck's constant. It's not the usual that we usually use, but you can use it. So E would be equal to 4.0 times 10 to the minus 13 kilojoules second per mole, right? Multiplied by 4.57 times 10 to the 14 hertz, or you could put per second. Now per second cancels seconds. So we're left with E being equal to, where the calculator at? 4.0 times 10 to the minus 13, right? Times 4.57 times 10 to the 14, and that is 182.8 kilojoules per mole. You can just put 182.8 kilojoules for the energy. If you want, you can convert it to joules. That would be times 10 to the 3 or times 1,000, and you'll get joules. And yeah, that was it for that question. Now, for the moles question that I gave them, this was, I think it's a GCSE question. Yeah. So a student titrates a standard solution of barium hydroxide with nitric acid, HNO3, which is 25 cm cube of 0.0450 mole per dm cube of barium hydroxide are needed to neutralize 23.35 centimeter cube of nitric acid. So first, what you want to do is actually write your equation for this. All right. So what's happening here is we have barium hydroxide, H bracket 2, plus nitric acid, HNO3, yielding H2O, which is water, and BaOH, bracket 2. So to balance the equation, but before I balance it, the reason why, how you could know what the products would be is you could identify that this is a base and an acid, and a base and an acid gives you salt and water. All right. So balancing. 2 here and 2 water, it should be good. Now, here it says a student titrates a standard solution of barium hydroxide with nitric acid, full stop. 25 centimeter cube of 0.045 mole per dm cube of barium hydroxide needed to neutralize 23.35 centimeter cube of nitric acid. Now, what we know is 0.0450 moles of barium hydroxide is in 1,000 centimeter cube. 1 dm cube is the same as, or is equivalent to 1,000 cm cube. All right. And now we want to know how much would be no barium. Oh, sorry. Yes, that's true. Barium nitrate. Thank you for that. NO3 would be the salt. So the salt would be barium nitrate and water. Thank you, Annalie. Now, here we want to know how much would be in 25 centimeter cube, since it's 25 centimeter cube of barium hydroxide that we need to neutralize the nitric acid. So 25.00 centimeter cube. Now, what you're going to do is cross multiply, so you end up getting 1,000 cm cube times that number of moles is equal to 25 cm cube times 0.0450 moles. I'll just put that into the calculator. 0.0450, and that's 1.125, right? So 1.125. Now divide by 1,000 on both sides, and I don't have to put this in the calculator. I could just write it in standard notation, 1.125 times 10 to the minus 3 moles of barium hydroxide. All right. Now, based on the equation that we wrote, it reacts in a 1 to 2 mole ratio. That is 1 mole of barium hydroxide reacts with 2 moles of nitric acid. Okay. So then we can find out how many moles basically of nitric acid was used in the experiment. So 1 to 2, we can just write it like that. And then 1.125 times 10 to the minus 3 moles would be equal to some amount of moles of HNO3. All right. Everything would be fine. Anyways, you don't have to write out everything because you can just look at it and see that you would get 2 times that 1.25 times 10 to the minus 3. 2 times that divided by 1, and you would get 2.25 times 10 to the minus 3. Now we know how many moles of nitric acid was used. Now we need to know the, what we call it now, the volume in order to calculate the concentration. We're told that it neutralized 23.35 centimeter cube of nitric acid, but they want the answer in moles per dm cube. So you have to convert centimeter cube to dm cube. How I do it, and most times I don't get it wrong, is I would write 23.35 centimeter cube, and the transverse to that, I would write centimeter cube over decimeter cube. Now, 10 centimeter is equal to 1 decimeter, and seeing that we're cubing, we just cube the numbers. 1 cube is 1, 10 cube is 1,000. Anyways, you'll end up dividing by 1,000 here. And so you would end up with 23.35 times 10 to the minus 3 decimeter cubes. Centimeter cube would cancel centimeter cube. All right. And so that would be the volume in decimeter cube. Let me get a bit more space on this so I can just work out the last part. Please. All right, I think that's fine. All right, so now concentration in mole per dm cube is basically putting the amount of moles you calculated, which was 2.25 times 10 to the minus 3 moles. Right? Over the volume that you just calculated in decimeter cube, which is 23.35 times 10 to the minus 3 decimeter cube. And that would give you a concentration for the HNO3. And so that would be 2.25 times 10 to the minus 3 divided by 23.35 times 10 to the minus 3. And you should get 0.096 moles per dm cube. And you're fine. All right. Oh my God. I remember, I think I tried to make this test challenging, but no, it's here kicking me in the gut. All right, so a chemist, this is a CXC past paper. I don't remember the year though. Past paper question. I think it's one of the earlier years, either 2007 or 2006. Now, a chemist is given 1.08 grams of a compound X and is asked to determine the molecular formula. Now, analysis of X by mass spectrometry gives a relative molecular mass of 108. Now, elemental analysis shows that the compound contains carbon, hydrogen, and one other element, right? Among the products obtained when X is burned completely in oxygen are 1,340 centimeter cube of carbon dioxide and 448 centimeter cube of NO2. I think that's nitrous oxide. Anyways, now what I usually do is I write out an equation. So I'd say CX, HY, And seeing that NO2 was also a product, one of the other element would be nitrogen, right? Because remember they said that compound X contains carbon, hydrogen, and one other element, which they didn't tell us, but technically they did. It's right here, nitrogen, plus O2, right? Burns in to give carbon dioxide, nitrous oxide, and water. The H comes from the hydrogen here, all right? Or the water, basically. Now, what do we know? First of all, you know that 1,340 centimeter cube of carbon dioxide was produced. You also know that 448 centimeter cube of nitrous oxide is produced. Now, and you also know that compound here, compound X is 1.08 grams, right? So now you're basically heading towards mole ratios, right? So first of all, know that seeing that the gases are measured at STP, pay attention to that. 1 mole of a gas by Avogadro's law would be 22,400 centimeter cube, right? Which is 22.4 decimeter cube. Oh my God. So if we know 1 mole is equal to 22,400 centimeter cube, how many moles would be in 1,340 centimeter cube of carbon dioxide? That's what you want to find out. So I just say X moles, and 1 mole is equal to 22,400. Cross multiply, you'll find that you would say 1,340 centimeter cube divided by 22,400, and that would give you 1340 over 22,400, and that would be 0.06. I rounded up, by the way. And here you have NO2, you have 1 mole being equal to 22,400 again. And you would say 448 divided by 22,400, and that would be 22,400, 0.02, right? And you can also find the mole ratio for this here, the unknown compound, because we know that 1 mole of the compound is equal to 108 grams, seeing that the molecular mass is 108 grams. Thus, let's say Z is equal to 1.08. So you'd end up getting 1.08 over 108, and that would give you the answer for that. So let's just do that real quick. And that's 0.01. Again, you want to divide by the smallest ratio that's there. So the smallest number of moles that's there, so 0.01, right? And I don't have to put this in the calculator, but you'd see that this is 1, this is 6, and this is 2. So you can put 2 here, 6 here, and you know that 1 mole of that. So 1 mole of the, yeah, sure, I can scroll up. So you'd find that 1 mole, tell me when I can scroll back. You'd find that 1 mole of the compound that they actually use mass spectrometry or was combusted in the reaction would actually give, was it 6 moles of carbon dioxide and 4 moles of NO2. I can scroll back down now, Sarah. I'm gonna scroll. Yeah, so 2 moles of NO2. I think I said 4 and I'm incorrect. So it's 2 moles of NO2. All right. Now that we know this, we can actually start writing our formula or molecular formula. So C6, because we have 6 carbons, and I'm not sure how much hydrogen yet, so I'll just put back HY, sorry, and N2. Now, seeing that I know that the molecular mass is 108, and I know most of the number of moles of each atom in the molecule, I can just say 108 minus 12 times 6 plus 2 nitrogen, which is 14 times 2. And that would give me 8, I think. Let's see, 108 minus 12 times 6 plus 14 times 2. Yes, 8. Therefore, the remaining thing is 8, which is 8 hydrogens. So you can just simply put that in and you got your molecular formula, which is C6H8N2. All right. I'll send you guys the paper. Just message me. This was a redox question, I believe. So dry cells, batteries, dry cells, those are batteries, yes. They provide a portable source of energy for many modern appliances. So the figure below shows some of the components of a dry cell, which you have here, the cardboard covering, brass, copper alloy. But the fact that they stated copper here, they want you to use copper in your answer, not brass. So pay attention to that. And which is the positive contact. Graphite rod, the ionic paste, the zinc casing, which is your negative contact, or you can say negative terminal, whichever you're more comfortable with. All right. And the question, part A of 3 asks us, all right, so referring to the information in the figure above, explain why the chemical reaction occurring in the batteries is described as a redox reaction. Now, the reason why it is described as a redox reaction is because the zinc provides circuit with electrons. So is oxidized. So whichever one loses its electrons is oxidized. So you can think of, remember the little thing there, oil rig, the acronym thing. Mnemonic, that's what it's called. Oxidation is lose or loss. Oxidation is loss, while reduction is gain. So the one that loses its electrons is oxidized. So zinc would be the one that is oxidized to Zn2 plus ions. And the copper ions were copper 2 ions, which is a Cu2 plus. In the ionic paste, right, are reduced to copper solid. And that's why it's called a redox reaction. One thing is reduced while the other is oxidized. All right. Now it says to write the half equations to represent what will occur at the anode and the cathode. So reduction occurs at the cathode while oxidation occurs at the anode. And And acronym, or another mnemonic, I don't know why I keep saying acronym. So red cat, so reduction at the cathode, so red cat, and I just know that the other one is oxidation. I know this oxidation, one of my students said anox. Yeah. So for the anode, we want to write the thing in terms of oxidation, right? So we need to figure out which one of the elements would be oxidized versus which one would be reduced. Now, the most often, the one that's oxidized is the one highest or higher on the reactivity series. So in this case, zinc would be the one that is oxidized, seeing that it's more reactive than copper for one. So it's higher in the reactivity series, as well as it's the one that supplies electrons to the cell and circuit, right? So you want to write Zn solid, then gives you Zn 2 plus 2 electrons. Now, for every equation, I usually stress this a lot. You can know if your equation is balanced if the charges are the same on both sides, as well as the amount of a species, right? So here you have one zinc, that's fine. Now, zinc here on its own has no charge. But over here you have a +2 charge. So that's why you need 2 electrons, because one electron has a charge of -1. So by multiplying that by 2, you'd get -2. And if you add, if you sum +2 and -2, you're going to get 0. Therefore, the charge is balanced, so everything is all right for your equation, right? So you can use these little tricks to test if your answer is correct. Now for the cathode, where reduction occurs, you will have the Cu2 plus ions, can say aqueous, right? Plus 2 electrons will give you Cu solid, right? And you will realize that for every half equation that you write, for the reduction, the electrons are on the left of the arrow, while for oxidation, the electrons are on the right of the arrow. Most times. So that would be your answer for that question. Now, here we go. So when sulfur dioxide gas is bubbled through acidified potassium chromate, the redox reaction which occurs can be represented by the following half equations. And here we go. All right, we have 7H2O. There was a mistake there. So if you're writing this down, remember to put the 7 back in the formula. I guess I forgot to type it out, yes. Yeah, so 7 should be there. Now, whenever I see questions like this, I locate the electrons first. So here we have 2 electrons and here we have 6 electrons. Now, what you're going to do is look if they're on opposite sides of the arrows. So down here, it's actually on the left, and here it's on the right. So I don't have to flip any of the equations. So I'm all right? Now, the next thing I want to do is actually get the number of electrons on both sides equal, or in both equations equal. So to do this, what I'm going to do is multiply this entire equation by 3, right? So let's write it out. Oh my God. So 3 SO2 gas plus 3,2 is 6 H2O liquid gives you 3 SO4 2 minus aqueous. 2 3s 6 electrons, and 3 4 is 12 H plus ions. No, I didn't do any multiplication for the bottom thing because it's already 6. So I'm just going to write back everything. So Cr2O7 2 minus aqueous, remember your state symbols, plus 6 electrons plus 14 H plus ions will yield 2 Cr3 plus ions, and in its aqueous form, of course, plus 7 H2O, right? And you want to cancel out the things that are there. So first of all, electrons, the 6 electrons will cancel out. No, there aren't any SO2s down bottom, so that's fine. However, there are H2Os, but there's 6 up here and 7 down here. The 6 waters up here will cancel the only 6 of the waters down bottom, so you'd be left with 1 H2O. All right, so keep that in mind. Now, what else do we have in common? We have the H plus ions. We have 12 up here, so 12 will cancel only 12 of the 14 here, so you'd be left with 2 H plus ions. All right, and so when you write out the complete balanced equation, what you would get is 3SO2 gas plus whatever is down here on the left of the arrow, Cr2O7 2 minus aqueous. That's here we have two H plus ions plus 2 H plus ions. Remember your state symbols. And on this side, we have 3SO4 2 minus aqueous, right? And 2 Cr3 plus. That's aqueous as well. And that would be your fully balanced equation, right? Now, let's move to the other question. It says state the change in oxidation number in any one identified reagent in the reaction. And so chromium in the Cr2O7 2 minus, it has an oxidation number or oxidation state of +6, and that is reduced to Cr3 plus, right, in the reaction. And you have sulfur in the SO2 molecule that had an oxidation state, if you work it out, of +4, and it is oxidized to +6 in the SO4 2 minus. If you don't know how to work this out, let me show you. So here, let's work out the oxidation state of chromium in the Cr2O7 2 minus ion. All right. First, write out your things so you can see it. So Cr2O7 2 minus. Now write an algebraic expression for it. So 2 Crs plus oxygen would be they have 7 oxygens, but the oxidation state on oxygen is 2 minus. So you can say -2 times 7. Jesus Christ. So omega +6. Anyways, is equal to -2. So 2 7s 14, you get -14 here, being equal to -2, 2 Cr. And the 2 Cr is going to be equal to -2 plus 14. You have to bring over the 14, so you flip the signs. So 14 minus 2 is equal to 12. Oh, okay. I did do it properly. So here we go. They divide by 2 on both sides to get chromium by itself. 2 into 12 is equal to 6. So that's how I got +6. All right. Now this here, section B, okay, I divided it. So this wants you to explain how, this will deal with module 2 topics, by the way. So this wants you to explain how the following factors may affect the rate of a chemical reaction. So first, a catalyst. What a catalyst does is it reduces the activation energy, first and foremost. So reduces the activation energy. And that creates an alternative pathway for the reaction to actually progress or propagate. And how this helps to speed up the reaction is that when this alternative pathway at a reduced activation energy is created, you'd find that there are more particles in the reaction that are able to actually reach the energy required to kick off the reaction, right? Because think about it. If the activation energy is lower, most particles or some addition of the particles inside the reaction vessel will not have to be at the activation energy that was needed first, right? So if you have something lower, that's totally fine as long as you meet the requirements. So you have more particles that are able to actually participate in the reaction because of the reduced activation energy. Now for 2, it says concentration of reactants, right? Now, if the concentration of the reactants are increased, right, what you'll find is there will be more particles present in the reaction. And thus, you will have more frequent and more successful collisions, right? And the opposite is true. Is true if the concentration of the reactants is decreased, right? And that would be it for that. I think I actually modified this question. It was a past paper question, but I modified it. Now here we are with the rate of reactions. I didn't do anything to it. I didn't change anything. It's the exact question. Now the reaction between peroxide disulfate and iodide ions yield the species I3- in accordance with the following equation, right? They give you the equation to look at. And I guess you just look at the equation. Table 1 gives some experimental data from an investigation of the rate of reaction between the peroxide disulfate ions and the iodide ions, right? And the rate equation can be represented as rate is equal to K is equal to the concentration of the peroxide disulfate ion, and the M power times the concentration of the iodide ions to some power, right? So you need to examine the table and actually understand what it's saying. So in the first experiment, initial concentration of the S2O8 ion is 0.5, and by the second, experiment, it was 0.10, and it didn't change in the third. And for the iodide, it's 0.1 in the first experiment and 0.1, it didn't change in the second experiment, and 0.5 in the third experiment, so it decreased, right? Pay attention to that. Now, R1 means the initial rate of the reaction for experiment 1 was 1.5 times 10 to the minus 5, and this is 3 and 1.5, all right? Now, let's look at what the question wants you to do. The first question wants you to determine the order of the reaction with respect to the peroxide disulfate ion and the iodide ion. So let's do the peroxide disulfate ion first. Good. So you want to look at the column with the iodine, or the iodide ion rather, and see where it has been constant. So here, 0.1, 0.1, right? It's constant. Now look what happens to the S2 OA 2 minus ion while the iodide ion is constant, the concentration, right? It moves from 0.05 to 1. Obviously, it's doubled. But if you can't tell, what you can do is put the second number over the first number. So you can write 0.10 or 0.05 and put that in your calculator and find out if it's doubled or halved or quartered or, increased by a factor of 4, whatever. But this is going to give you 2, so you know that it's doubled. So you write 2 to what power would be equal to, now look what happens to the rate. What happens to the rate is it starts out at 1.5 times 10 to the minus 5, and it goes to 3.0 times 10 to the minus 5. Again, this is doubled because 15, this is practically looking at it, 15 plus 15 is 30. So that's how you can, if you can look at numbers like that and just tell, it's fine. If you can't, just use the thing that I just showed you, you just do R2 over R1, and you see that it's doubled, all right? Now, see that we said that it's doubled, that's it. So 2 to what power would give you 2. So in this case, X would be equal to 1. Therefore, the reaction with respect to the S2O8 2 minus ion is first order. So let me just write that down real quick. First order. Great, we get another chance to look at how I just did that by looking at the I minus, right? Promise you'll get it right every time. So here, look over at the other column, find out where it is constant. So we have here and here. So we'll use these two numbers here for the iodide ion. Now we see that it moves from 0.1 to 0.05. This is halved, right? Again, to figure out this, if you can't just look at it like that, you can say 0.05, which is the second number, over 0.1. Put that in your calculator, you're going to get a half. Now you're going to say half to what power is equal to, this is 3.0 times 10 to the minus 5. We're looking at the rate now, causes this rate to decrease to 1.5 times 10 to the minus 5. And that's also a half. So half to what power gives you a half? 1. So here, X is equal to 1 again. So with respect to the iodide ion, it is first order as well, right? Simple. Now, this wants you to calculate the overall order of the reaction. The overall order of the reaction is the sum of the individual order of the reaction. So we had first order for one, and the other one was also first order. So the overall order of the reaction is second order. All right. Now state Le Chatelier's principle. Le Chatelier's principle. Swat this. If you don't understand it, swat it. When a system, I don't advise swatting it, but if you have to come down to that, just swat it. So when a system experiences a disturbance, what you'll find out is that the system will try to counteract it, will try to counteract the change or oppose it, I guess. Oh, forgot the change, in order to restore its equilibrium, right? Yes, and that's the Chatelier's principle. So if you increase the temperature, what the system will try to do is decrease the temperature to restore its normal state where it was before, all comfortable. If you increase the pressure by Le Chatelier's principle, the system will shift, or the equilibrium, sorry, will shift to the side with the lesser amount of moles in order to restore equilibrium. Because, all right, the whole pressure thing is kind of hard to think about. So think about a balloon or two balloons attached end by some tube. All right. Let's say you have 5 objects in this, while you have only 1 in here. And let's say you force another one in here. What will happen is, by this increased pressure will cause these that you have in excess to flow over here until you have some balance within the 2 balloons, right? So basically to create more space for itself. So that's what happens there when you increase the pressure. So by increasing the pressure, it moves to the side with the less amount of moles. All right. So let's continue. Now, this wants you to explain the concept of dynamic equilibrium. And dynamic equilibrium is achieved when a reversible reaction occurs. All right. So what you'd find, another characteristic that you'd find is that once you have an equilibrium established, and you'll find it by these 2 arrows, you will have the rate of the forward reaction. We're talking about dynamic equilibrium. So the rate of the forward reaction will be equal to the rate of the backward or the reversible reaction. All right. And that's all there is to it for the dynamic equilibrium stage. Now, looking at this, all right, past question, but I modified it. I changed the equation. I changed it to the Haber process equation. So using, I think the original question had the contact process or not. Sulfur was in it. I don't remember exactly, but I changed it. So using the equation N2 gas plus H2 gas, yields, ammonia, and it can be reversible as well. Explain the effects of the following on the equilibrium of the system. First thing you want to take note of is delta H. Is it negative or positive? Signs tell you whether the reaction is exothermic or endothermic. It's positive, it's endothermic. It's negative, it's exothermic. So this delta H here is negative. So we can infer that the forward reaction is, let's just write Rx in. The forward reaction is exothermic. All right. So let's move on to seeing what our question wants. Wants to know what will happen to the equilibrium of the system if we decrease the temperature, right? By decreasing the temperature, that means you are making it colder or more endothermic, right? So by decreasing the temperature, I think about it like that, what will happen is the system will try to raise the temperature. So it's going to do the opposite, right? Or try. And thus, the forward reaction is favored. Because remember, the forward reaction is exothermic. So you're moving hot, right? So the forward reaction is favored. And which way is the forward reaction? The forward reaction is to the right. Therefore, the equilibrium shifts to the right. All right. So you could include all of these in your answers, And what else will happen? The yield of ammonia will increase. Now, if you increase the pressure, remember, by Le Chatelier's principle, the pressure, by increasing the pressure, it will move to the side with the lesser amount of moles. Over here, you have a total of 4 moles of reactants, because you have 3 hydrogen here and 1 nitrogen molecule. Now here we have 2 ammonia molecules. So of course, by increasing the pressure, you will find that the equilibrium will shift to the right as well. So I'll just go ditto. And the state that the equilibrium will shift to the side with the lesser amount of moles, right? Hope you guys getting this now. And finally, a catalyst. Now, this is a trick question because a catalyst, it doesn't affect the equilibrium, right? Does nothing to the equilibrium, right? What a catalyst does is speed up the rate of the reaction. So you will still have even though the reaction rate has sped up, you will find that the concentration of the reactants is the same, going to always be the same, while the concentration of the products is going to be the same, all right? It's just happening at a faster rate. So nothing happens to the equilibrium. Now, this is a question about buffers. Now, a buffer solution is made by adding 6.56 grams of sodium ethanoate, and that CH3COO Na is the ethanoate ion, right? The sodium ethanoate molecule, sorry. And it's added to 1 dm cube of 0.0 mole per dm cube. That big M stands for molar, it's molar per dm cube of ethanoic acid, which is CH3COOH. Now define what a buffer is, or a buffer solution. Now a buffer solution is an aqueous solution or an aqueous mixture of a weak acid and the salt of that acid, all right? That's your buffer solution. Now the next question wants you to calculate the concentration in mole per dm cube of the sodium ethanoate in solution. Now we know that it's 6.56 grams of sodium ethanoate. So let's get to working on that. Now 1 mole of sodium ethanoate is equal to carbon. How many carbons do we have? Let me just write this back. CH3COO sodium ethanoate, right? We have 2 carbons, so 12 times 2 plus 3 hydrogens plus 16, which is 32, times 2, right? And 23 for sodium. So 1 mole is equal to 24 plus 3 plus 32 plus 23. That's 82, I think, yeah. And X is equal to 6.56 grams. So cross multiply 82 grams times X is equal to 6.56 grams times, 1 mole, right? And divide by 82 grams on both sides, right? And you'll find that X is equal to, calculator please, 6.56 over 82, 0.08 moles, right? And they told you that this was placed in 1 dm cube of solution. So the concentration is 0.08 mole per dm cube, but you can just, to be sure, you can, I don't know why I said to be sure, because it's over 1 dm cube. So there you go. So the concentration of CH3COO, which is sodium ethanoate, is equal to 0.08 mole per dm cube, right? Now, they want you to calculate here we go. Ka for ethanoic acid is equal to 1.8 times 10 to the minus 5 mole per dm cube. Write the Ka expression and use it to, for ethanoic acid, sorry, and use it to calculate the pH of the buffer solution. Now, Ka is equal to the products of the products, or the product of the products divided by the product of the reactants. Now, product, the first product I said is the multiplication part. So by multiplying the products and dividing it by the multiplied reactants. So in this case, if you write out your equation to see what's happening, CH3COOH when placed in solution will dissociate into CH3COO minus and H plus ions. Now you don't have to, but you can assume that the concentration of H plus is equal to the concentration of the ethanoate ions, and say H plus ion squared over the concentration of CH3COOH, right? Which is the acid. And now to work out the pH of the buffer solution, you'll need to know the Henderson-Hasselbalch equation, which I think is, pH is equal to pKa plus the log, we use base 10, of course, of the concentration of the salt over the concentration of the acid, right? I think we're okay. Now, if you don't know pKa is equal to minus log to the base 10 of Ka. So I can put that into the equation and say pH is equal to minus log to the base 10. You don't have to write it though, the 10 part. If you want to, write it down here as a subscript of Ka plus log of concentration of the salt represented by Ha minus and Ha, which is the acid, right? Now put everything into the you can just substitute now. So pH is equal to minus log to the base 10 of Ka that they gave us, which is 1.8 times 10 to the minus 5. You don't have to write the units into your equation because it can become quite cumbersome if you do. And log to that, which is the concentration of the salt, which we worked out to be 0.08 over the concentration of the acid that they said earlier. I think it was 0.02, but I can go back and check. 0.02, yes. Jeez, how far did I go? 0.02. And here we go. Put that all in your into your calculator, and you say minus log to the base 10. I think you have to put the 10. Yes, you have to put the 10 in your calculator. Minus log to the base 10 of 1.8. So bad. Minus 5 plus log to the base 10 of 0.08 over 0.02. All right. And my calculator is telling me 5.3. Let me put that again and check. 1.8 times 10 to the what? Minus 5 plus log to the base 10 of 0.08 over 0.02. Yes, 5.3 is your pH. I hope you guys are working with me. Yes, that's true. The buffer solution is one that resists a change in pH when a small amount of alkaline or acid is added to it. Yeah, that's correct. Great, 5.35. Yeah, I guess that's acceptable as well. So the group 2 elements, this is module 3, guys. I'm almost done. So we're only going to deal with a group 2 question and a transition element question, and then we'll be done. I'm so sorry this was so long, but after this, I got to get studying for my exam. So group 2 elements, beryllium to barium, right? Be to Ba, yes. And their compounds show distinct trends or patterns in properties and behavior. Now, this wants you to write an equation for the first ionization energy of barium. Now, it's best to know the definition for ionization energy, which is the energy required to remove an electron from 1 mole of a gaseous atom to produce, 1 mole of its gaseous ion. So the first ionization energy for barium would be Ba, this gaseous state. Remember that? So Ba plus, I know you're used to seeing barium in its 2+ state, but seeing that this is the first ionization energy, only 1 electron is removed. So you would just want to say plus 1 electron, and that would be the equation. And the state for the ion would be gaseous as well. And that would be the equation for the first ionization energy of barium, okay? All right, so using the data booklet provided, explain the trend in ionization energy with the atomic radii for group 2 elements. Now, first of all, as you go down the group 2, the atomic radii, oh my God, they increase, right? Therefore, the valence electrons are getting further and further away from the positively charged nucleus. So positive nucleus, far away electrons, right? And let's just VE, valence electrons, right? This then leaves us to deduce that, seeing that the electrons are getting farther away from the positive nucleus, the force of attraction between both the valence electrons, right? And the positive nucleus, because it's positively charged, seeing that protons are in the nucleus along with neutrons, but neutrons don't have a charge. So the net charge on the nucleus is positive. That's the reason, right? So the force of attraction between that is less as you get further away from the nucleus, right? So less energy will be required to remove an electron. Now it says write an equation for the reaction between one of the group 2 elements and water. So before I give you an example, let's say that the group 2 element is X arbitrarily, right? X in its solid state plus H2O liquid will give the group 2 metal oxide and H2 gas. All right? So let's use calcium as an example. So calcium plus H2O liquid would be CaO, right? Calcium oxide and hydrogen gas. And you're fine, you're supposed to get 2 marks. All right. I don't want to say yes. All right, sorry. Is log and log to the base 10 the same thing? No. No, because you can have log to other bases, right? But in your syllabus, you only work with base 10. So that's why it's okay to just write log, because we know it's still base 10. All right. Here, I don't even know why I put this question, but I liked it because it called for some reasoning and it would help them with the calculations for, moles, because that was a challenge for most of them. So I needed to upplay the weak areas or give them practice in their weak area as well, giving them practice, for their exam. So here says calcium hydroxide is slightly soluble in water at as room temperature rises, the solubility decreases. Now, when the maximum amount of solid has dissolved at a particular temperature, the solution is said to be saturated. Now, in the experiment, the solubility of calcium hydroxide was measured over a range of temperatures. Now, the results are shown in the figure below. Use the data from the graph, right, to calculate the concentration in mole per dm cube of a saturated solution of calcium hydroxide at 30 degrees Celsius. All right. So you want to go see a graph and look for 30 degrees Celsius and draw a line all the way up, right? And then all the way across. Crap. Why did I put the line right there? You're blind or something? What it's supposed to be. Never mind. It was correct. This will blind me. No lie. Oh, it's right here. There. So somewhere between those lines. Now, each square, every 5 little squares, yes, that is 5. It's 0.0 0.01 divided by 5, and you find that it's 2 times 10 to the minus 3 for each of these little squares. So this would be 1.5, 0. Let me get my pen. First of all, reading off this thing is the first thing you want to tackle, reading it off. So 0.5, and we went up by 2 tiny squares, so 2 times 10 to the minus 3. I'll just multiply that by 2 when I add it. And I'm just going to make an approximation right there because I'm not going to try to decipher what between that box is. All right, so 2 plus 0.15. I got 0.154, right? So let's just go down to the lines. So at 30 degrees Celsius, we found that the saturation was 0.154 grams per 100 centimeter. It's shown on the graph per 100 centimeter cube. So it's shown right there, so pay attention. Right? And they want the answer in mole per dm cube. So first hurdle, convert grams to moles. All right. So 1 mole of calcium hydroxide, OH bracket 2, is equal to calcium is 40 plus 16 times 2, because the 2 is out here, plus 1 hydrogen times 2, 1 for hydrogen times 2. And so you get 1 mole of that being equal to 74 grams, right? And X would be equal to 0.154 grams. That's what we want to find. Remember that. So cross multiplication occurs, we'll end up dividing 74 grams by this. And we will get 2.08 times 10 to the minus 3 moles of calcium hydroxide, right? Now we know that this amount, 2.0 times 10 to the minus 3 moles, is per every 100 centimeter cube. So we're gonna have to do some conversion. So let me change the color of this pen so you can follow properly and don't get mixed up. All right, nice. 2.08 times 10 to the minus 3 moles over 100 centimeter cube, because that's basically what that means, right? And you want to convert the centimeter cube to decimeter cube. So put centimeter cube on top over decimeter cube that you need to get, right? Here we go. 10 centimeters equal 1 decimeter, but seeing that we're cubing everything, right? Remember that step. We'll end up having centimeter cancel centimeters, and what we'll find is then we will multiply by 1,000, 2.08 times 10 to the minus 3 times 1,000, which is the same as 10 to the 3, and divide that by 100, right? That's down here. So multiply that by 1,000 and then divide it by 100. And you should get 0.02, right? 208, let's just do that for now, right? Since we already did that, and I want to give the answer to three significant figures, so this would be an answer in mole per dm cube, right? So the concentration of calcium hydroxide, right? At 30 degrees Celsius is 0.0208 moles per dm cube. And that's how you calculate it. Had a bit of conversion, but with practice, it's no problem. Based on the trend in group 2, explain how the solubility of the group 2 hydroxides in water change as you proceed down the group. Now, the hydroxides, the solubility of the hydroxides, they increase. Yes, they increase as you go down the group, right? And this is because the hydration energy or the hydration enthalpy, whichever word you want to use, you can use energy, enthalpy, whichever one like you prefer, nobody really cares, decreases, right? It decreases going down the group. And what you'll find is in relation to the lattice energy, according to something we call the square factor, right? You'll find that the lattice energy decreases faster than the hydration enthalpy. And that would be the reason why the solubility of the group 2 hydroxides increase going down group, right? And this question wants you to explain the difference in the trend of the solubility of the group 2 hydroxides in water versus group 2 sulfates, right? Now, for group 2 sulfates, it's practically the opposite. So for hydroxides, it increases because the lattice energy decreases, pay attention to this, right? Decreases faster than the hydration enthalpy. And for the sulfates, as you go down the group, solubility decreases. And this is because the hydration energy or the hydration enthalpy, it decreases faster than the lattice energy. And yeah, so just pay attention to those two differences. They're basically opposites. Now, 7, finishing 7, and we're done for the day. Promise. All right. So for the most part, most of the elements in the first row of the D block are considered transition elements. I think I made up this question. With the exception of scandium and zinc. Explain the reason for this exception. Now, transition elements I'm just gonna say trans elements. They are elements that form stable ions which have a partially filled d orbital. Yes. Need to find my paper. All right. And the thing is, scandium 3+, which is like most common ion for scandium, it has no electrons in the d orbital, right? If you write out the electronic configuration, you'll see it. So it has no electrons in the d orbital. And for zinc, most times you see the 2+ ion, of course, you will see that the d orbital is completely filled. So that's why they aren't considered transition elements, all right? Because it has to be partially filled, not completely filled, that is, right? At this point, this scandium not start full up yet in, Jamaican terms, and zinc take everything and it filled. So that's why they aren't. Now, explain the reason for the colors exhibited by transition metal complexes. Now, off the bat, think about D to D transition, right? You don't need to know in depth about this, but D to D transition is basically when an electron gets excited and it just raises itself to another d orbital, right, of a higher energy. So what happens is when light is incident on a transition metal complex, I must say transmetal complex, right? The electron gets excited. And it moves to a higher d orbital, right? Or a d orbital of higher energy state. And higher energy. Eventually, when the electron loses the energy it had absorbed before, so becomes de-excited or de-excitation occurs, they emit photons or energy of wavelength and frequency in the light or visible light region, right? Visible light region of the EM spectrum or the electromagnetic spectrum. All right? So that's basically why it's colored. And the whole thing about how we see light, the colors we don't see, they are absorbed, while the ones we see are the ones that are reflected onto the retina. Now, transition elements exhibit special characters which distinguish them from group 1 and group 2 metals. So for example, transition elements exhibit variable oxidation states. This is one characteristic. Now determine the oxidation states of vanadium or VO2 minus, vanadium in the VO2 minus ion and the vanadium in the VO2 plus, right? Let's deal with the VO2 minus first. So VO2 minus. Again, write an algebraic expression for this. So V plus minus 2 times 2, because there are 2 oxygens, is equal to, the charge here is -1, even though we don't write the 1. And you'll have -2 times 2 being -4. Vanadium plus that is equal to -1. Want to bring over this -4 to the other side of the equation. So V is going to be equal to -1 plus 4. Thus, vanadium is equal to +3. in here. Now, for the VO2 plus, you want to do the same thing, write an algebraic expression VO2 plus, right? And thus you'll have V plus -2 for the oxygen, but there's only one, so we cool with that. So, and that's +2 as well, is equal to +2 because that's the charge. And V is going to be equal to, you have to bring over this -2 to the other side of the equation. So you're going to get V is equal to +2 +2, and that's equal to +4. So in that case, vanadium in the VO2 plus ion is equal to +4. And you're done with that. Now state 2 other characteristics of transition elements, right? Now, 2 other characteristics of the transition elements can be that they have catalytic properties, so they can be used as catalysts. So vanadium pentoxide, V2O5, is used as a catalyst in the contact process. And that's used to produce sulfuric acid, right? Girl, I have chem exam next week. Please remember which catalyst used in the Haber process. Haber process. Iron, or is it nickel? I think both. Nickel oxide at one point, and we have an iron catalyst added at another point in different stages. So we have both iron and a nickel catalyst in the Haber process. And yeah, anyways, the transition element in this is vanadium. And for the nickel, it's nickel, and iron is iron, right? So also they can form colored metal complexes. All right, and we're good with that. I think there's just one more question. Yes, that's the last question. We are here. Transition metals have higher melting points than metals such as calcium in the S block of the periodic table. Now, this has to do with the size of the cations and, the ions or the atoms, really, that the transition elements possess. Now, the trend in this is that from like the first transition element to about chromium, the sizes of the size of the atoms decrease, then they start to level off. Then when you get to about copper, Cr3+, it starts to increase back until you get to zinc. All right, so that's like the trend that you will see. Now, right here, when you're thinking about melting points and boiling points, you need to think about intermolecular bonds. Now, it's important that you know the difference between intermolecular bonds versus intramolecular bonds, all right? Intra means within, so think about bonds such as metallic bonding, ionic bonding, covalent bonding. That involves intramolecular bonds. We're talking about intermolecular bonds, talking about the weak van der Waals forces along with other London dispersion forces, right? We're talking about hydrogen bonding. We're talking about, well, you have any more? You probably do. Anyways, in this case, like for something like water, let me explain something to you. When you're boiling water, not many people have thought about it, but I'm sure you know this. Let's say we have a stove and water is in your pot, fire under it. So at one point it's gonna start to boil. What you'll find is steam is still H2O, right? So you don't have the hydrogen breaking apart from the oxygen, but rather what you have happening in boiling is that the H2O molecules are breaking apart from each other. So the hydrogen bonds between the different water molecules are breaking and allowing, to leave the surface of the water. All right. So that's it. Now, in this case, you have to think about transition metals and how they bond, right? And this would be more metallic bonding. So you need to think about what would make the metallic bonds stronger. And in this case, two reasons why the transition elements or the transition metals would have higher melting points than metals such as calcium in the S block of the periodic table is because of the stronger metallic bonds that would be formed. And this would be because of, let's say, transition elements have larger atomic numbers than the calcium here, right? So that larger atomic number signifies that the number of protons is more, right? And with more protons and more delocalized electrons, number of delocalized, the attractive forces in the sea of delocalized electrons versus the metallic cations, those make for stronger metallic bonds. And of course, because calcium would have less than the transition elements, it would not require as much energy to break its bonds, all right? So that's why the melting point of the transition element is actually, what do you call it? Higher than calcium. Another reason is because of the size of the ions, right? The size of the ions. And in this case, we're talking about the size of the cations, right? Now, remember I told you that the trend for the atomic and ionic radii for these transition elements is where you have it decreasing, then it goes constant until it starts to increase again. But for an element like calcium, I think the atomic radius for calcium is around 220 to 231 picometers, while for titanium, it's around 200 to 218. So it's less than calcium. That's my point. So and if titanium would be one of the first transition elements, right? And from there, going across the period, the atomic radii decreases, what you'd find is that, of course, all of them would be smaller than calcium. Thus, the smaller ions would make for stronger, what do you call it? Metallic bonds. And yeah, those are the two reasons you can explain, you get your marks. So yeah, all good. So I guess that's it. Scroll up back to the zinc question. Which one of the zinc questions? The transition element zinc question? This zinc question? Yeah. So I guess that's it, I guess. I think I'll just add this paper to my drive and just put the link below the live stream when it posts itself, so you guys can get access to it. But yeah, I guess that's the last question. So I'm gonna end the stream now. Sorry, I'll message you with the thing. Would you look at that? I can stop sharing.